Previously, we've talked about functions and function calls. And we said that one function can even call another function. And we saw this with a user-defined function calling something like the print function. Well, a user-defined function can, of course, call another user-defined function. We saw this in our function module. And in fact, a function in most programming languages can even call itself. This is a process called recursion. Now, sometimes recursion is direct recursion, where you have function, let's call it foo, and it calls foo, which it calls foo, which calls foo, etc. Likewise, you can have indirect recursion, where you have function A call function B, which calls function C, which calls function A, which calls function B, which calls function C, etc. And so not through a direct recursion where the function calls itself directly, but maybe as simple as A calls B, B calls A, or A calls B, which calls C, which calls A, or you might have several other functions mixed in there. That's referred to as indirect recursion because it's not directly calling itself, it's called a function that eventually will call itself. So in this module, we're going to look at recursion and some potential problems we might run into with it and how we're going to solve those problems. Let's get started. So here I have my main function and the little if statement to check to see if we need to call main. Let's look at how we're going to use this. So I'm going to create a function that's going to be called counter. Def counter. And I'm just going to put in, I'm inside counter. Okay, pretty simple. Then I'm going to call counter. So this is what's going to make it a recursive call. Then up here inside my main, I'm going to call counter. So this is my initial calling of counter. And then after that, it's going to be a recursive call. Now, what you'll see is when we run this, we're going to run into an issue. And if you saw real quickly, you notice it printed out, I'm inside counter. And I did this several times, and then it created an error. That error was because we can only make so many function calls at one time. This is simply known as a stack overflow. So what happened is we ran into an issue where the call stack overflowed. Now you might go, well, what is a stack? What is a call stack? Okay, so let's explain that concept to you real quickly. Whenever you call a function, internally it says, okay, I am going to put all of my previous functions information and I'm going to temporarily store them, kind of put them in a little storage. And now I'm going to have a new place for new variables and things like that. Well, that takes up a little bit of space on something they call a stack, and there's only so many slots in Python for that stack. This is how we can have separate variables in each function, even if they're named the same thing. So there's a limited number of slots that we can make our function calls in our call stack. When we get done with a function, that function gets removed, we go back up to our previous location, and now we have access to all of its variables and things like that. If it makes another function call, we go down one in the stack, and we now create a new place for its variables in that function. Under normal circumstances, this stack is more than large enough to handle your everyday function calls and functions calling functions calling functions calling functions. But if we get into an infinite recursion loop where we keep calling the same function over and over again and we never have a way to exit out, we can get into a call stack overflow. And that's what's happened here. So if we look at this, we get what's known as a recursion error, and it's a maximum recursion depth. Approximately 995 or so function recursion calls, and you're going to hit this error. Like I said, more than enough for normal operation. However, when we have a recursion, we can run into this. So let's see why this is happening. On line 7, you see we define counter. Line 8, we print. And line 9, we call counter. Well, we're inside that function and we create a new element on our stack. We go to counter again. So because we're using recursion, it doesn't go back to that previous one. Okay, it creates a new element on our call stack. And so we go into counter and it prints I'm inside a counter. And then we hit the counter call again, and so it creates a new one. We never actually exit from counter, because to exit from one function counter means that we have to have exited from the counter previously called, and we never do that. So whenever we're using recursion, we need to make sure we provide some sort of test that allows us to exit out of that call. So let's see a quick simple example of how we might do that. I'm going to create a variable called count, and I'm going to give it a default value of 5. So this way, if we don't have a value, we see it. Okay? Go to line 8, and then after 8, I'm going to hit the enter key, give me a new line. If count is greater than 0, I'm going to call counter. Okay, if it's 0 or less, we're not going to call counter. We're not going to make a recursive call, and it's going to exit. So inside my call to counter, I'm going to say count -1. It's going to do that first, then it's going to pass that value to my call for counter. CLS, run. Now you see, okay, it runs. First time, second time, third time, fourth time, fifth time, and sixth time. Okay, so you had the first time it was called when nothing was passing, count was therefore defaulted to 5, and it goes down. Okay, so this is the correct running of this application. Now you might be asking, okay, why did it print 6 times? Well, remember, when it was 0, we still printed I'm inside counter, but we didn't call the counter function. So let's see how we can kind of change that to maybe get more along what you were expecting. I'm going to say print I'm inside counter. The count is counts. Now you're going to see it goes down to 1 and it doesn't print for the 0 element. Okay, that's probably what you're more expecting. And this is kind of interesting because notice it's counting down. But I want to show you how the order of how you call your commands is very important. So I'm going to take line 9, going to remove it and put it on line 10. So we're just swapping lines 9 and 10. This way we're calling counter and then we're printing. Okay, so if I run this now, you notice that it counts up. You might say, well, wait a second, how come it's counting up? All you did was move that one line down. Well, first time we said I'm inside a counter, the counter is 5, then we call count. And when we called counter, it was count -1, and so we said we're inside a counter, the count is 4, and then we call count recursively. And as we called counter recursively, those numbers went down in value. However, with this counter, because the print statement is after the call to counter, what happened is the count is equal to 5. So we said, okay, the count is equal to 5. Then we call count -1. Okay, well, that made it equal to 4. And then we say, okay, if 4 is greater than 0, it is. Counter is count -1, 3. Remember, each function has its own variable. Even if the variable has the exact same name, each function call has its own set of variables. And so we had 5, then 4, then 3, then 2, then 1. And then once we said, oh, count is, 0 is not greater than 0, okay, we're going to exit out of that count function. It's going to come up, and now after that counter there on line 9, we're going to go to line 10 and we say, okay, I'm inside counter. The count is 1. And then that exited out of that counter. And so it went up the call stack. So as we were going up the call stack, we saw that the printout appears to make the numbers go in increasing order. So simply changing where things work can have a big outcome on the way things run. Okay. This also is a great way to prove that every time you call a function in Python, now, not all languages are like this, but Python is, as are most modern languages, you have your own complete separate set of variables, and those are not shared. Okay, so this is a great way to kind of see that. Okay, so let's clear the screen. So I want to look real quick at how we can use recursion. And for this, I'm going to go very simply and show a factorial. If you're not familiar with factorials, if I say 5 factorial, that means 5 times 4 times 3 times 2 times 1. Okay, 10 factorial is then 10 times 9 times 8, and you kind of get the idea with that. So I have here a very simple factorial function, and inside of it we use a loop. Okay, so we define our initial factorial value. We say while num is greater than 1, and then we do factorial times num number minus itself by 1. Okay, so very, very simple, and I can come in here and say print 5 factorial is, then I can say factorial 5. And if I run this, you're going to see that 5 factorial is 120, and that's correct. And I can come in here and say, well, okay, 15 factorial, if I run that, 15 factorial is a very big number, okay? And that is actually true. You know, factorials get very large very, very quickly, okay? So we don't tend to see them too big. Computers do run into a certain amount of problem with how big a factorial can get. That's a whole different story. All right, so let's go back to factorial 5, just for simplicity's sake. Now, this is a very simple way of doing a factorial, but we could also do a factorial with recursion. You might say, how would you do it with recursion? So we need to make sure that there is a nice error check to make sure it's not a negative value. So I'm going to say if num is less than 0, we're just going to return 0. Now, some books will give this as it's an error, it's an invalid data, you can't do it. We're just returning 0 just because. Okay. Elif num is equal to 0. We're going to return 1, else. So this is a great combination of using our if condition statements. We have 2 checks that we're doing for special cases. Notice that none of them are calling factorial recursion. Okay, so this makes sure that we have a chance to exit out of it. Now what are we going to do? We're going to say return num times factorial recursion of num minus 1. So this is going to reduce us. So if we have, let's start off with something simple, 2, okay? So if we pass in 2, it's going to check, okay, if num is less than 0, nope, equals 0, nope. Okay, so it's going to be 2 times factorial recursion of num1. Num1 is 1, okay? Then it's going to go and say, okay, let's subtract 1 from it again, and then we're going to do, and it's going to return 1, not have factorial recursion, and we exit out, so it's good. You could kind of tweak this, get a little bit more efficient, but this is pretty simple. And we're making sure we're multiplying by that last 1, even though it's not technically required because anything times itself is itself. But like I said, just for simplicity's sake, we can see it. Okay. So this allows us to have our factorial recursion. It allows us to have our built-in check. Okay. So remember our first 2, we return without calling the recursion. We don't actually return until the entire line of code is run. And so we have our initial number times, and then we call it recursively. So we're going to come up here, and I'm going to say factorial recursion. And I'm going to pass in 5. We should get the exact same value. I'm going to do a clear screen on my terminal window, and I'm going to click run. And notice that 5 factorial is, notice they both give the exact same value. That's exactly what we were hoping for. So as you can see, you might think, well, when can recursion be used? Well, maybe when loops are used. And typically, almost any loop can be done recursively, and almost any recursion algorithm can be done with a loop. So why are there 2 different ways? Well, remember I said almost any. There are a few examples where we can't necessarily do that. Or at least I've not found a way to, within a loop, programmatically be able to do a recursive algorithm. So we need to know that sometimes we are stuck due to limitations within the programming language, one way or another, that we need to use a loop or we need to use recursion. Typically, recursive calls are going to be a little bit slower because remember that call stack, we have to go and create a new element on the call stack, set up all of its variables, do all that stuff. So typically, our recursive calls take a little bit longer to run. For some problems, though, recursion is easier to understand. And so if it's easier to understand and it is fast enough, then we typically will use recursion. Remember, part of the mark of a good programmer is writing code that other programmers can understand. And simple recursion is something that most programmers should understand. So that's just a simple example where you might see. Now, some other places you might see recursion are in other mathematical concepts. You might take a look at things like fractals. And fractals have a lot of interesting relevance inside of our natural world. So if you don't know what a fractal is a subset of mathematics. And a fractal talks about patterns that look similar to themselves. If you look at things like your blood vessels, you'll notice that how you have off of one blood vessel, you have arteries that branch out, and off of that you might have sub-arteries, and they go out and they branch out further and further and further. You can see that, and that is an idea of a fractal. It's a naturally repeating pattern. We see this in a lot of different areas, whether it's in how trees are formed and how you can branch off and to have smaller branches, and smaller branches can have smaller branches. You can see it in a leaf and the pattern of how the water will flow out through capillaries to the edges of the leaf, etc. So there's a lot of interesting places that it's seen. Some of them are just purely mathematical constructs. Some of them, like I said, are good for representing nature. There are other purposes for them as well. Fractals tend to need to be shown using a recursive algorithm. You'll see it in other mathematical components as well, such as maybe the Fibonacci sequence. The Fibonacci is based upon the previous two values. So my new value is based on my previous two values. And so I can create a function. So I'm going to call my function fib just so it's a little bit simpler and easier to write. If num is less than or equal to 0, I'm going to return 1. Elif num is equal to 1, return 1. Now, Michael will always say, why are you doing that? Well, remember, it's based off the two previous. So if I said it was less than or equal to 1, I may not get the appropriate results I was looking for. So this just makes it a little bit easier to understand. Else return fib num minus 2 plus fib num minus 1. So we're going to go and call the Fibonacci sequence minus 2. Whatever number was passed in, we're going to get it minus 1. So what we should see is 1, 1, 2, 3, 4, etc. So I could come up here and say for I in range 10, print fib I. And this will help us to print out our values. Rewrite it. You notice 1, 1. 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8. 5 plus 8 is 13. 8 plus 13 is 21, etc. And this prints it out nicely so you can see what each of those values are. Now, typically what you'll find is that your Fibonacci sequence works really well, but it's going to start to slow down pretty quickly. And you might say, well, where is that? Well, typically in the 30-35 range. Now, it may be more or less depending upon how fast your computer is, how much RAM you have, some other factors like that. but you have so many recursive calls because remember, in order to find out what the previous number was, you have to run through the whole Fibonacci sequence again. So this can really start to slow you down. So let's just make a couple minor changes here. I'm going to say I, comma, just so we can kind of see, okay, what's the value and how big the number is getting and how much slower it's taking. We're just going to look at this visually. We're not going to actually do any type of performance counting. But you can see that as I got to 28, it was no problem, but 29 started to really slow down. 30, 31, 32, 33, as it gets longer and longer, the amount of time it takes really increases. So this is a potential issue you run into with recursion. Now, there are some nice little features that we can use inside of Python to make it much faster. So what we're going to do is we are going to use a special caching tool. How is that? Well, I'm going to go to my very first slide and I'm going to import an external module. So I'm going to say from functools import LRU cache. Now, LRU cache is a special type of cache. There are other caches depending upon what version of Python you are using that might be available to you, what other libraries you have available, but we're going to look at LRU. So LRU cache, what we need to do is here, after our function, we're going to say at LRU cache, and we need to give it a size. The bigger the size, the more is cached, the faster our response will be. But whenever we cache something, we're remembering what was returned from that function. That's great, but we have to store it someplace, which means that it's faster, but it's going to take more memory. It's a trade-off. We have to figure out, okay, what trade-off do we want to use? So I'm going to put 10 in, and just remember what it was like beforehand. Now if I run, did you see it? It's done. Do it one more time. I'm going to do a clear screen just so you can kind of see this in terminal and make sure you know, like, you know, oh, you didn't really do it. Yeah, watch this. Okay, so it's clear. We're going to run. And by simply caching some results, it's almost as fast as way back when. In fact, I can maybe make it 135, which before would have just been outrageous. There's no way you could have done it. But now it's almost as fast. It's because it's remembering what those previous values were. So it doesn't have to go in and recalculate everything. And that's simply with an LRU cache of 10. Okay, if I put 100, it would have been even faster. Would it have been fast enough to really make it worthwhile? Probably not. Okay, not for the trade-off. So sometimes you can do a relatively small LRU cache and still be much, much faster. This is something that's unique to Python. Not caching, but this functional returning values, this LRU cache. So this is just a good way to kind of, you know, think about, oh, this is going slow, but I'm using Python. Oh, I've got this neat little tool that I can use to make my life a lot easier and faster. So always keep that in the back of your mind. If you're having to do recursion and it's seeming to take forever, this is a nice solution to it. If we had done this without the LRU cache, we would have gone, got some lunch, come back, and it still would be running, it would seem. Okay? So knowing what you're trying to do, knowing the tools that you're using can really make a huge improvement in your performance. And that's just what I want to show you here with your Fibonacci sequence. Because a lot of your fractal patterns too, if you're going to be doing applied mathematics with fractals, they have lots of recursive calls and they can really start to slow down. Or you can do something like this and start to get a lot more efficient. So just something to keep in mind when you're working with recursion.